Okay, so we're going to continue discussing the von Neumann entropy today. So yesterday we defined the entropy to begin with, where we said that S of rho is simply negative trace rho log rho for any density operator rho on the Hilbert space H, right? This is the basic definition. So we said that one way to evaluate this is in terms of the eigenvalues . So lambda I are the eigenvalues of rho . In other words, rho has a spectral decomposition or eigenvalue decomposition of this form where EI are the eigenvectors, right? So the EI, of course, constitute an orthonormal basis for the space in terms of which you can evaluate the trace, right? So this is an equivalent way of defining the von Neumann entropy, right? And while there are several properties that we need to discuss, at the heart of all of them turns out to be this positivity or non-negativity of the relative entropy, which we discussed yesterday. So let us revisit that. So the sort of important theorem that we discussed yesterday is, so we first defined the relative entropy. So right after defining the von Neumann entropy, we defined the relative entropy between two states. Right? And this was defined to be trace rho log rho minus rho log sigma, right? But if you want to write it as two separate terms, you can write this as trace rho log rho minus trace rho log sigma, and this is the same as minus of the von Neumann entropy of this minus trace rho log sigma, right? And what we proved yesterday is so-called Klein's theorem. It says that the relative entropy is always non-negative with equality if and only if rho is equal to sigma. So this, therefore, can be thought of as a distance measure between states, between density operators on the Hilbert space, right? Okay, so what do we want to discuss today? We want to discuss a few more properties of the von Neumann entropy. So a lot of these properties, as you know, will follow as corollaries to the positivity of relative entropy. Okay, so let's first do simple properties and then move on to more interesting things. Okay, so first is, this is always positive, okay, with 0 if and only if, yes, what is the condition? We already discussed this yesterday. When is the von Neumann entropy 0? Sorry? Yeah, I can't hear you very well, Nilka. But anyway, I guess that you said that rho must be a pure state, right? So how can you show that it is always positive? That simply comes from the fact that you can evaluate it to be minus sum over I lambda I log lambda I, where lambda I are the eigenvalues of this density matrix rho. Since the lambda I are such that they must sum to 1 and they are real positive quantities, right? So this must then mean that the lambda i's lie between 0 and 1, right? And when I take the log of something that lies between 0 and 1, then this is negative and the lambda i's are real positive. So negative log lambda I is positive. So I'm taking the product of um, two positive quantities. And so what I end up with is something that is positive. Okay. So this is done and it is a pure state if and I mean it is 0 if and only if it's a pure state, because a pure state is essentially like having a single eigenvector with a single eigenstate. So rho is psi psi, right? Then what this means is that it's essentially like a single eigenvalue which is 1, right? It's essentially a state with a single eigenvalue which is 1. And so then essentially the lambda distribution that you have is like a delta distribution as far as your probability in the probability language is concerned, right? The second thing is what is the maximum value, right? So what is the maximum and when is it attained? So for a d-dimensional Hilbert space, S of rho is always less than equal to log d with equality if and only if rho is equal to I by d, which is the maximally mixed state on the space. So for any d-dimensional quantum system, the maximum entropy that you can have is log d. And how do you prove this? Well, the same way that you prove the maximum value of the Shannon entropy is log d to the base 2 for a d-dimensional probability distribution or probability or random variable which can take d possible values. The way you do that was by evaluating a certain relative entropy, right? So here also take the relative entropy between two density operators. One is some arbitrary density operator rho and the other is I by d. So first of all, note that I by d is a valid density operator on the space, right? So why is it a valid density operator? It is a positive operator. It is basically, so if I have any orthonormal basis, for the d-dimensional space, then I by d is simply sum over I, 1 by d, EI, EI, right? So these EI, EI are all rank 1 projectors. They're all positive. 1 by d, the coefficients are all positive. So this is a positive semi-definite operator. And what is its trace? Well, its trace is 1 because this is essentially a diagonal representation, right? Identity is diagonal in any basis that you write it in. So if you take the sum of these diagonal entries, you get 1, right? So this is a valid density operator. This is just an aside to keep in mind. So when I'm taking this relative entropy, I know that this has to be positive. That comes from the theorem that we proved yesterday. So let us expand the left-hand side. The relative entropy between rho and I by d is nothing but trace rho log I by d. I'm sorry, trace rho log rho minus trace rho log I by d, right? So the first term there is obviously just the entropy S of rho itself, right? Sorry, just give me a second. Okay, sorry, there was some interruption here. Okay, so the first term is just trace rho log rho minus trace rho log sigma. Yeah. Was there a question? Somebody's raised hand. Okay, so this is just minus S of rho minus, so what is this term out here? How do I expand log of I by d, right? It is basically, so this is what I'm going to claim. So what is this operator log of I by d? This is, like we said, log of this operator, right? But that is nothing but, so this is already a spectral decomposition of I by d. So this is nothing but an operator whose eigenvalues are all the same as the eigenvalues of this operator. So that's log 1 by d ei, right? So do you see this? Okay, if there are questions about this, ask me, but this is the crucial step. And then that's it. So you have minus S of rho minus trace rho times sum over I log 1 by d ei, right? That's what you have. I'm just going over the steps slowly so that, like I said, you can do these problems yourself in the future. Now, what is happening here? Log 1 by d is just to fix the same for all the i's, right? So I take that out. So I can, in fact, take that out of the trace also. So that's just negative log 1 by d trace of rho times sum over I ei. What is that? Sum over I ei out of
identity.
Exactly. And then trace rho. So trace rho is 1. So this is just minus S of rho plus log d is greater than equal to 0, which then means that log d is always greater than equal to S of rho, or S of rho is always upper bounded by log d. Okay, so this is the argument to say that this is always this relative entropy, I'm sorry, to say that the Shannon entropy is always bounded from above by log of the dimension of the space. And in this case, equality happens when these two are equal, right? So that simply follows from the Klein's theorem itself that we proved yesterday. So equality, if and only if rho is exactly equal to I by d, and that is done, right? So that is the maximally mixed state. So we have shown both limits of the Shannon entropy, right? Lower bound, the lower bound is 0, the upper bound is the dimension of the space itself. Okay, the next property that I want to discuss is subadditivity. But before that, I want to talk about, yeah, so this is an interesting property. So let me note this. So suppose, now consider, so let's start considering joint density operators on two systems. So let us consider a bipartite density operator, because ultimately strong subadditivity has to do with that only, right? You have to talk about joint entropies. So if I talk about joint entropies or two random variables, in this case I have to talk about two density operators on two different Hilbert spaces. But before that, let's look at a bipartite density operator, which is a density operator on HA tensor HB. So I have two quantum systems A and B, and this is the bipartite system, and consider any density operator on HA tensor HB. So I'm going to now say two things. So if rho AB is of the form some rho A tensor rho B, okay, which means, so or let me say this as sigma A tensor phi B, okay, then this entropy, yes, is nothing but S of sigma plus S of phi, right? So how do we show this? Is there an easy way to see this? So we just have to go back to the definition, right? And when you go back to the definition, you see that what you have out here is now, you simply have to diagonalize this, right? So let's say that sigma A is of the form SI, SI are its eigenvalues, let's say, EI, and phi B is of the form sum over, say some other J, let me say Pj, Fj, right? So now how will I define the entropy of this joint state? That is nothing but minus trace rho AB log rho AB, right? But now this is already, so this is, remember, these are the spectral decompositions of the individual subsystem density operators, right? So I don't know if I've used this word before. So each of this is called a subsystem, right? So there are two subsystems here. Sigma A is one subsystem density operator, phi B is the other subsystem density operator, right? So then this is the spectral decomposition of the individual density operators on their own subsystems, right? But if I put that together, since rho AB is simply the product form, sigma A tensor phi B, this becomes sum over ij Si Pj EI tensor Fj. I hope you see this, right? But now this is an orthonormal basis for HA, right? This is an orthonormal basis for HB. So if I take the tensor product together, I get an orthonormal basis for the joint system. So this is Si Pj EI EIFJ, EIFJ. And this is an orthonormal basis for, and when I say this, I mean the set EIFJ, this set of vectors, right, which is simply EI tensor Fj. I'm putting both of them together into one ket. I hope we've all seen things like this in the last semester, and I hope you recall all that, right? So this is an orthonormal basis for HA tensor HB. So now what is this joint entropy, or the entropy of this bipartite or joint state of A and B? It is simply negative sum over ij Si Pj log Si Pj. So now this is as if this lambda ij, which are, so these lambdas which are the eigen values of rho AB, are simply products of eigenvalues of sigma A and phi B. Okay. So this should remind you, so it should remind us of what? Two independent classical. Yeah, exactly. Good. So it should remind us of a pair of independent classical random variables or independent probability distributions. And there you know that the entropy of the joint distribution is simply the sum of the entropies of the individual system. You see that clearly coming out here, because now I'm going to say log of Si times Pj is simply log Si plus log Pj. So I separate out the two terms. Then I simply sum over. So here I do the sum over I. If I sum over all the Si, that should give me 1. Here I sum over all the Pj, that should give me 1. So I'm simply left with sum over I minus sum over I Si log Si minus sum over j Pj log Pj. Si are the eigenvalues of sigma A and Pj are the eigenvalues of phi B. So this is nothing but the von Neumann entropy of A, and this is the von Neumann entropy of the state in B. And so the entropy of the joint state is simply the sum of this when rho AB is simply a tensor product of this form. Okay. So in some sense, we proved part of the subadditivity statement, because obviously now the subadditivity statement will be to ask what happens to this joint entropy if A and B are not, if the state is not simply a tensor product of A tensor B, right? We will come to that. But before that, let's look at another interesting case. So is this clear that the entropy of a tensor product is simply the sum of the individual entropies? That's all we need to take away from here. I'm going through steps, maybe somewhat laboriously, I don't know. But the hope is that everyone is following with me. Okay. The second aspect of bipartite density operators that I want to talk about is this. Suppose rho AB is actually psi AB psi AB. In other words, rho AB is a pure bipartite state. Then what can we say about the entropies of the subsystem density operators? Yes? Anybody? I'm sure some of you are doing project on entanglement entropy and all of that. So when I have a pure bipartite state, we learned a technique last semester which allowed us to expand a pure bipartite state in a particular way. Okay, so let me state the result. So then the entropies of the subsystem density operators are equal. In other words, S of A is equal to S of B, whatever be this marginal state in A and whatever be the marginal state in B. Note that in this case, we are not saying that A and B are, that it's a tensor product state. Okay. We're not saying that it's a tensor product state. So it could be some kind of entangled state, right? So what is the, when something is not a tensor product state, when something doesn't factor out like that, then obviously it means that there is some correlation or there is some entanglement between the two subsystems, right? So what is the proof or the argument for this? Whenever I have a pure bipartite state, I have what is called a Schmidt form. what does the Schmidt form say? It says that there exist local bases EI and Fi such that this can be simply expanded in this form, right? Sum over I lambda I EI Fi. Actually, I think I should say square root lambda I to be consistent. So then what you would have shown last semester is when I take the reduced density operator. So what does this statement mean? It means that the entropy of the marginal states are equal, right? So the marginal states have equal entropy. Right? That's what this means. So what is the marginal state here? How do I calculate the marginal state? I have to trace over B of psi AB, right? And what will this be? You can already read this out from here. So please go back and look up your notes on Schmidt decomposition and all that. But what you'd have shown is that the two reduced states, this is now trace over A, psi AB, these two reduced states simply have the same, what? They have the same eigenvalues. The eigenvectors may be different because they are on different spaces, right? This is on HA and this is on HB. But they have the same set of eigenvalues, and that is what matters as far as the entropy is concerned. Therefore, from the fact that you have a Schmidt form, one can show that S of rho A is the same as S of rho B, which is equal to minus sum over I lambda I log lambda I. So this so-called subsystem entropy, so this is often called the subsystem von Neumann entropy, right? When I have any joint state, it need not be a pure state, it need not be a tensor product state. So we've looked at two cases. We have looked at the case where this is pure but could be entangled, right? After all, what does the Schmidt form tell you? It tells you that these are the two bases in which the state is entangled. And if there is only one non-zero Schmidt coefficient, then you know that the state is not entangled. This is all something we discussed last semester. So we've considered the case where this is pure but entangled, or where this is a product of two local density operators, which means it is still mixed. It's still a density operator, but product or unentangled. Right? So these are only two cases, right? Now, of course, the most general case where it could be mixed and entangled. Right? So this we will come to, and that is where the subadditivity property will come now, right? But these are the two cases we've looked at, and what we are studying in both the cases, we are trying to express the joint entropy in terms of the subsystem entropies, or we're trying to get to some property of the subsystem entropy. So this is what is called the subsystem von Neumann entropy, and this, at least in this case of bipartite pure states, can be used as a measure of entanglement, right? So this constitutes a measure of entanglement for bipartite pure states, right? And that goes back to the Schmidt form, because if this S rho A is equal to S rho B is equal to 0, then it means that there is only one non-zero lambda, right? That's the only case where you get zero entropy, which means there is only one term in the Schmidt decomposition. Which in turn means that this is a product state. So no entanglement, right? So this in turn implies that psi AB is simply of the form sum E1 tensor F1. That's all. Right? So this is product unentangled. So if it is non-zero, then you know that the state is entangled. So if rho A, which is the same as the entropy of B, is greater than 0, then there must be more than one non-zero Schmidt coefficient. There must be more than one non-zero lambda. In that case, rho AB is truly entangled. Right? So all of this we've sort of seen earlier when we did Schmidt decomposition, but it may be useful to recall this. So yeah, but always note that when I have a pure bipartite state, then the entropies of the local subsystems are equal, right? And if they're both equal to 0, then the state is entangled. If they are both non-zero, then the state is entangled. Now note an interesting property, that if I have such a, and this is the last thing I want to note, and then I'll go to the subadditivity statement. So in the second case, where psi AB is entangled, right? What is the entropy of the joint state? Yes. Rho AB is a pure state, right? So what is his entropy? What is the entropy of the joint AB system together?
It should be 0, right? Pure state.
Indeed. So this is the entropy of a pure state. And so this should be 0. But what is the entropy of the reduced states? If it is an entangled state, then we just said that S rho A is equal to S rho B is greater than 0, which means that the joint entropy is actually less than the individual entropies. It is less than SA and less than SB. Now, this is a scenario which does not happen in the classical setting at all, right? Because we very coolly stated a property yesterday that the joint entropy, if you remember these Venn diagrams that we drew, then the joint entropy was always the individual entropy plus a certain conditional entropy. Correct? If you recall these Venn diagrams that we drew yesterday, then I said if this whole thing is S of A, then what is S of AB? It was this whole thing, right? So it included SA plus this part, which was simply the conditional entropy of SB given A. So we see a clear departure from the classical case now, where you can have a situation that you have a state, you have a joint state, which has 0 entropy, but its marginals somehow have non-zero entropy. Not only can they have non-zero entropy, but they can have maximal entropy. So this is a clear departure from the classical Shannon entropy, where this can never happen, right? It's like saying that I have a joint distribution, which is a delta distribution, and then somehow the marginals of this delta distribution have become more spread out, right? Not only have they become more spread out, like I said, you can have an extreme version of this. And what is the extreme version of this? When will I have an extreme version of this? By that I mean, you know, we can have S rho A is equal to S rho B is equal to log D, while S rho AB is equal to 0. When is this possible? For what kind of states?
X maximum.
Sorry?
When the individual subsystems are maximized.
Yes, so what kind of states are these? Give me a simple 2-qubit example. Exactly. So when psi AB is a maximally entangled state like a well state. Okay, so all of this basically follows from noting that the subsystem entropies are saying something about the mixedness of the local systems. The joint entropy is saying something about how mixed the joint state is, and it's possible that the joint state is actually pure, whereas the subsystem states are maximally mixed. And this is what happens indeed when you have a maximally entangled state. So this is why we say that entanglement is a situation where you are more certain about the whole. So you have more information about the whole than about the parts. Somehow it's like when you take out the parts, your uncertainty just becomes more. In fact, it can even be maximal all the way up to log D, right? Okay, so both of these were properties related to bipartite density operators, right? One where you said that for a product state, the entropy of the tensor product is the sum of the entropies. For a bipartite pure state, the local subsystem entropies are equal. And we saw that the joint entropy need not always be greater than the individual entropies. You can have states where this joint entropy can actually be less than the entropy of the individual states. By the way, it does not mean that this is always the case also. Basically, what it means is that you don't have a neat relationship between the joint and the local entropies. You can have any which way. You can have, of course, states where the joint entropy is greater than the individual entropies, states which behave more like classical distributions. And then you can have this scenario where this happens. Okay, so maybe let me note one thing right away here, that if I were to define a conditional entropy, so let me note this as a, I think this is the third property. This is 3, okay. So I want to talk about a conditional entropy. So what is a conditional entropy? This is SA given B. Like in the classical case, we define it to be the joint entropy SAB minus SB, right? Similarly, you can define the other conditional entropy S of B given A is basically again the joint entropy minus SA. By the way, for the joint entropy, sometimes you will see people writing this as A comma B. Here I've just chosen to write it as AB. Doesn't matter, it's the same. Again, different notations, that's all. Okay. Now, what can you say about the conditional entropy? In the classical case, the conditional entropy was always positive. But quantum conditional entropy can be negative, right? So that's again a very interesting departure from the classical case. And this exactly happens for the case of these entangled states, right? So the classic example of this is when my bipartite state is one of the Bell states, right? So then the local entropies are maximal, which is log 2 to the base 2, which is 1, right? But the joint entropy is actually 0. But so you have a kind of really negative conditional entropy in this case, because your joint entropy is less than both your subsystem entropies. So your conditional entropy in this case is actually -1. Okay, so this this negativity of the conditional entropy can be thought of again as a signature that there is entanglement in the system. And again, this is a clear indication that this entanglement is a kind of phenomenon which cannot happen in the classical case. You simply cannot have a negative conditional entropy scenario. That's just in the nature of these distributions and the entropies in the classical case. But the quantum entropy is such that there can be states, or quantum mechanics admits states for which these kind of rules can be violated. This is yet another such example of something which is very fundamental property in the classical case actually becomes is just not true, right? So this can be negative, and indeed it is -1, right? Actually, the statement you can make very precisely is that for pure bipartite states, again, this goes back to the Schmidt statement that we just made earlier. For pure bipartite states, the conditional entropy is negative if and only if psi AB is entangled. So it is indeed a signature, you can think of it as a sort of witness for entanglement if your conditional entropy is negative, right? So it's an if and only if condition for only for pure states, right? Mixed state entanglement is always a harder thing to characterize. So we'll come to that next, actually, where we start talking about mixed states or arbitrary bipartite density operators. So anyway, I hope no questions so far, right? We've discussed pure bipartite states. Local entropy is always equal. Local entropy can be maximal, whereas the global entropy is 0, the joint entropy is 0. In fact, what that means is that the quantum conditional entropy can be negative, and this can be a signature of entanglement for bipartite pure states. Now, what about this general bipartite states? What can we say about the joint entropy versus the individual entropies? So this is where this notion of subadditivity comes in. So you have S of rho AB, and you want to know how it is related to the two marginals, the sum of the two marginals, rho A and rho B. And the statement is that the joint entropy is always less than or equal to the sum of the individual entropies. And this is the same statement in the classical case, and it turns out that this exactly goes through in the quantum case as well, right? The special case that we saw was that of equality. So equality if and only if rho AB is simply the tensor product of its marginals. In other words, it's a mixed state, but a product state, right? So long as the joint state is a product state, the joint entropy will simply be the sum of the individual entropies. Again, this is the classical analog of independently distributed random variables. So these are uncorrelated states. Or rather, the two subsystems are uncorrelated. So let me say this is a scenario where the subsystems are uncorrelated, or they are in a state which has no correlation between the two subsystems. Okay, so how do we prove this subadditivity statement? So this is the most general statement you can make about an arbitrary bipartite state. So once again, you have a certain signature of entanglement here. And what is that signature of entanglement? It basically is whether rho AB is equal to SA plus SB or not. So if the subadditivity is a strict inequality, then you know that the state must be entangled. It cannot be a product state. Because if it were a product state, subadditivity would be satisfied or saturated with equality. Okay. So once again, we can write down the difference between the right-hand side and the left-hand side, and that will be the mutual information quantity, just as what we discussed for the classical case, right? Okay, so let's prove this. The proof again is simply invoking relative entropy, positivity of relative entropy. So once again, this has to do with non-negativity of relative entropy. How so? Well, consider rho AB, and if I trace over A, I get rho B, and if I trace over B, I get rho A. So consider the relative entropy between this arbitrary bipartite density operator and the density operator that you get by taking the product of the marginals. What does that mean? You take rho A tensor rho B. Now this relative entropy always has to be positive with equality if and only if rho AB is indeed just a product of its marginals. So this is the scenario where subadditivity is satisfied with equality. But if not, what happens? Let's write down again what the left-hand side is. So remember that you will get minus S rho AB minus trace rho AB log rho A tensor rho B. So once again, now you have to invoke the same properties of the log. Earlier, I wrote this down explicitly where I visualized this, each of this in its own local basis. And hence I showed you that the log will become the sum of the logarithms. I'm not going to go over the same steps again. I hope you will now agree with me that this is nothing but log rho A minus trace rho AB log rho B. Now, this seems like a strange object. This is a bipartite state on A and B. This is just log rho A. What does this mean? This actually means it is log rho A is the operator on subsystem A, tensor identity in B, and this means it is identity in subsystem A, tensor log rho B in subsystem B. So now what do we do? Remember, this trace is a joint trace over A and B. So you make it a reduced, you make it a partial trace, right? You make it a partial trace only for subsystem A. In this case, what do I want? No, I want to make it a partial trace only over subsystem B. Then here I simply have rho A tensor identity B. So this is where the partial trace will give me something non-trivial. It will give me the marginal rho A, right? So this simply becomes minus joint entropy minus, I do the trace over B first. This is exactly like in the classical case, you're summing over one of the two probability indices, right? You're summing over one of the two probabilities. So now this gives me trace A, rho A log rho A minus trace over B, rho B log rho B. So this is nothing but minus joint entropy plus SA plus SB. This is always positive. So this means that S of A plus S of B is always greater than or equal to S of B. Okay. And of course, we've already discussed this equality condition, equality if and only if rho AB factors into a tensor product state across A and B, right? Questions?
Excuse me, ma'am.
Yeah.
I don't understand. The trace was over the complete AB, right?
Mm-hmm.
Then how did you make it partial trace?
Yeah, so the trace over AB, when I do this, so let me write it. So this is rho AB times log rho A tensor identity on B, correct? So now I can first do the trace over B alone. Okay. When I do the trace over B alone, this becomes trace over A, sum over some basis in B, right? Rho AB. Of course, I have to write the whole thing here, log rho A tensor IB, etc. But the tensor IB, if I expand in the same basis, that's really not going to contribute anything. It's only going to pick out that basis element again. So effectively, this will become trace over B of this rho AB times log rho A. You understand? So you can expand this IB in the same basis, and then you put the trace over B on both sides. So you'll have another ket IB here. But I mean, you can make the sum over J maybe. And then it will pick only one basis. I mean, the I and J will become a delta. So there'll only be one sum, and that sum will simply be this. So this will become trace over A, trace over B of rho AB times log rho A. And trace over B of rho AB is nothing but the state rho A. So this becomes trace over A, rho A log rho A. Is that clear?
Yes.
Yeah, you just have to work this out. Expand your identity is as in whatever basis you're taking the trace in, and then you will see that it cancels out. In the sense, this is not going to contribute anything except that it will make this ket act on this rho AB. And so you will essentially end up with a trace over B of rho AB, and that is nothing but rho A. Okay? Yeah, just work it out. It should become clear. All right. So that was subarrativity, easy enough to show and a very nice property. Both classical and quantum entropy satisfy this, which is very nice. So this is, like I said, so now you can define something called the mutual information. So let us go ahead and define the quantum mutual information. This is like a simple corollary of the subarrativity statement. So this is, so again, I'm going to call this as I A colon B. And often you put a little row here to reference that you're taking the mutual, you're considering the mutual information of a particular state row. This is simply defined to be S of A plus S of B minus S of AB. So the subarrativity, of course, tells you that this is always positive with equality, which means equality means what? This mutual information vanishes if and only if the state is such that it is a tensor product of its marginals. So this quantum mutual information, you can also equivalently define it as a relative entropy is nothing but a relative entropy between the joint and the tensor product of the marginals. And this is always positive with 0 if and only if rho AB is equal to rho A tensor rho B, same thing. So this is a measure again of entanglement for arbitrary bipartite quantum states. By arbitrary, I mean that it need not be a pure state. The earlier measure that we had, which was the subsystem, just look at the subsystem entropy, and that itself being a measure, that was true only for pure bipartite states. Because it's only for pure bipartite states that you have a notion of a Schmidt decomposition, which then captures, which then tells you, gives some meaning to this subsystem entropy, right, in terms of the Schmidt coefficients and so on. But for bipartite mixed states, you don't have something like a Schmidt decomposition. So the subsystem entropy in itself may not tell you anything about the entanglement, right? Because you obviously you have a product mixed state where the marginals, I mean the local density operators need not have zero entropy, right? But just that fact does not make a mixed state to be entangled. So I hope you understand what I'm saying. I can have a rho AB, which is rho A tensor rho B. Okay. But then S of A is not 0 and neither is S of B. And neither are the two equal. Okay. So just S of the subsystem being greater than 0 cannot witness entanglement for mixed states. Okay, so I hope that idea is clear. So for mixed states, you need to go beyond just the subsystem von Neumann entropy. And that is why you need something which will tell you, in some sense, it's telling you the difference between the actual bipartite state and the product of its marginals, right? And that's why it's nice to have this relative entropy, which is actually telling you the distance between these two things. If they are the same, well and good. It's unentangled. It's clear. It's a product state. I can prepare the state locally. I can prepare, A can separately prepare the density operator rho A in her lab, and B can separately prepare the density operator rho B in his lab. And both of them can have non-zero entropy. But they're still not entangled. They're just product, independently prepared. But when rho AB is not equal to the product of its marginals, then the deviation from this, how far apart these two are, is what is captured by this relative entropy, or in other words, this mutual information. Okay, so that is why the mutual information forms a nice measure of correlations in a quantum state. Sometimes people just like to use this itself as an entanglement measure, but then the field is just, if that's all there was to it, then the field would be over and done with, but that's not all there is to it. So while this is a measure of entanglement, there can be other measures of entanglement which might make sense in other scenarios and so on. But the non-zero, the fact that the mutual information is non-zero clearly tells you that the state is correlated. There is some correlation across subsystem A and subsystem B. Okay. Questions? Fine. So this discussion on subadditivity and mutual information is exactly what we had with the Shannon entropy yesterday, right? So there's nothing changes in that regard. It's only when you discuss pure bipartite states that you can have a very strong deviation from the classical setting. You can have a joint entropy which is smaller than the individual subsystem entropies, and you can have negative conditional entropies. So this is one set of properties of the von Neumann entropy. Now let us try to understand what happens to the entropy under various sort of state transformations, right? These were all just properties of the entropy itself. Now let us ask. Yeah.
I don't understand, how did you write in mutual information is equivalent to that?
To this?
Yeah.
Oh, that is exactly what we showed, right? That is exactly what we showed with improving the subadditivity, right? Yeah. So I said this is rho AB. So what is the left-hand side? We basically proved that the left-hand side is this. By the sequence of steps, we showed that the left-hand side, where I started with the same relative entropy between rho AB and rho A tensor rho B, right? Just by doing the same, marginal trick, right? I showed that the left-hand side is nothing but minus SAB plus SA plus SB. And that's exactly the mutual information.
Yeah, yes.
That's all, yeah. So we already showed this. In improving subadditivity, we showed this. In fact, the proof of subadditivity is just the positivity of this quantity. And this quantity, you can either view it as a relative entropy between the joint and the tensor product of the marginals, or you can view it as the mutual information between these two subsystems. Okay? Clear?
Yes.
All right. Okay. Okay. So now the next thing is to understand how the von Neumann entropy behaves. So let me say, some of the secondary properties of von Neumann entropy, or how the von Neumann entropy transforms under state changes. So what do I mean by that? So let us look at one very standard example, which is to ask what happens to S of rho, or how does S of rho change so let me first discuss this under projective measurements. Maybe I should first say how it transforms under unitaries and then go to projective measurements. Let me see. Yeah, there's just so many things to discuss under this that becomes, I just want to make sure that I'm not missing out something. All right, let's just discuss projective measurements first. Yeah. So then I think unitaries will just take a couple of minutes. Should be easy enough for you to see what happens to the entropy under unitary measurement, unitary transformations. So what is a projective measurement? So I have my rho, right? So let's say, so consider a projective measurement. So let me call this P. Maybe it's called P. With a set of orthogonal projectors Pi. So for example, your Pi could simply be, this set could simply be a measurement in the 0-1 basis, right? Or it could be a measurement in the plus-minus basis, or more generally, in a d-dimensional system, it could be a projective measurement onto your standard basis, I going from 1 to d, etc. Right? So you know that typically when I draw this measurement box here and I'm measuring this projector P, right? My outcome is going to be one of these d possibilities. So here I said ket1, ket2, etc., ket d. But I, of course, will represent this as a map, right? So how does the state, so if it's a pure state, how does the state transform under measurement? Well, what I end up with, the collapse itself, I cannot model it as a map, right? That is simply that's simply a kind of it's just a collapse, right? It's just psi going to, excuse me, psi going to 1 or psi going to 2 or psi going to b or whatever. But the correct way to model measurement as a map, as we know, is to say that the output is an incoherent mixture of all possible outcomes, right? Set of all possible outcomes is all the IIs, excuse me, weighted by, in the case of a pure state, it's just weighted by these probabilities. So you can see for yourself, and we've done this before, that this is nothing but acting these rank 1 projectors on the state. Sorry, I need more space. So more generally, I will have psi getting mapped to sum over I, pi, psi pi, where pi are the individual projectors that constitute the measurement, right? More generally, if I have a density matrix, then that will go to this. So all of this was to just lead up to this. So this is the transformation we have to consider, most general transformation under measurement of a density operator. Well, under a projective measurement. Of course, we know there are things like POVMs and so on. So, but the projective measurements are an important enough class of measurements that we can try to first understand what happens to the entropy under just a projective measurement. So the statement is that one is going to prove is that the entropy cannot decrease. So the von Neumann entropy cannot decrease under projective measurements. So if rho prime is sum over I pi rho pi, then S of rho prime will always be greater than or equal to S of rho. So this should be clear enough to see. I mean, this is what you would expect, right? Because if I start from a pure state and then I collapse onto one of the possible outcomes, one of the possible eigenstates of the observable that you're measuring, then clearly you have gone from a pure state to a mixture of this kind, right? So you have gone from a scenario where your initial entropy was 0 to a scenario where your final entropy S of rho prime is now something clearly non-zero. It is negative of whatever this is. So if I call these as some lambda I, then it is lambda I log lambda I, which is clearly greater than 0. So this is an extreme case of this, where I start with a pure state, right, which has clearly gone to a mixed state after measurement. And so this is a sense in which measurement destroys coherence, right? So people like to talk about this in various ways. In quantum foundations, they will tell you about information disturbance trade-off. So when I measure, why am I measuring? I'm trying to get some information about the state, right? But in the process of extracting information about the state, I have disturbed the state. What is worse, I have destroyed coherence. I have gone from a pure state to a mixed state. Okay. So more generally, if I have an arbitrary density operator, one can show that under a projective measurement, I will always get a state which is more mixed than the initial state. I will get a state which is at least as mixed as the initial state, if not more. Right? So, of course, if I started out in an eigenstate of the observable itself, then this entire mixture will just collapse to one state, right? If I were measuring one of the ket i's, if my state psi was one of the ket i's or just ket j, then this inner product will become a delta function and I will just be left with a single state in the summation, right? So if that is a case in which your initial entropy was 0 and your final entropy was 0. But that's a very special case. So unless I am in an eigenstate of that observable itself, the quantum entropy will increase under a projective measurement. It cannot decrease. Okay. So let me state this formally. S of rho prime is always greater than or equal to S of rho with equality if and only if rho is equal to rho prime. Okay. Now, what does rho equal to rho prime mean? It means that, so let's first look at the equality case. So equality implies that rho is equal to rho prime is equal to sum over I pi rho pi. So what does this mean? Suppose I multiply on both sides with one of the pj's. Okay, so I will do pj rho. This is sum over I pj pi rho pi. Pj is one of the other projectors in the set. So what is pi pj? Because they are a set of orthogonal projectors, remember. So this is nothing but delta ij pi or pj. So then this becomes nothing but pj rho pj, right? So in other words, you're saying that pj and rho, so the pj acting before rho in some sense becomes the same as pj acting after rho, right? So rho then has to commute with all the pj's for all j going from whatever 1 to d if there are d orthogonal projectors in the set, right? So in other words, now this can happen, again you can convince yourselves, pj are orthogonal projectors. This can happen if and only if rho is diagonal, right? If and only if rho is diagonal in the measurement basis. Okay. So, which means that a spectral decomposition of rho will involve essentially the same set of projectors, right? That is when you can have the final state to be the same as the initial state after an orthogonal project measurement. Right? This is just a bunch of steps to convince you of that. So let me go ahead and prove that statement itself, and then we will wrap up for today. So what is this statement? That the final entropy is always greater than or equal to the initial entropy after a measurement. So this was just to understand the equality case. So let me write the general argument. Again, goes back to relative entropy. So just look at relative entropy between rho and rho prime. That relative entropy is positive or non-negative. So once again, this means that trace rho log rho minus trace rho log rho prime is greater than or equal to 0. This is minus s of rho, right? So let me take the minus s of rho that side. So this means s of rho is less than or equal to negative trace rho log rho prime. So all that remains is to show that this negative trace rho log rho prime is nothing but s of rho prime, right? And then we are done. So how is that? Well, so this is negative trace. What am I going to do? So I'm going to insert a decomposition of identity in terms of the PIs. So recall that sum over I PI must be identity, right? Because PI constitutes an orthogonal projective measurement. So when I sum, so this is like a completion of identity. So if PI were just rank 1 objects, then this is equivalent to this kind of a statement, right? Where I have this is equal to identity, right? So Yeah, so this is, so I just insert this identity here. So that will give me, so just bear with me for 2 more minutes and then we'll wrap up class. So this is sum over I pi rho log rho prime is once again pj rho pj. Okay. And now it's just a matter of playing around with the PIs and PJs to convince yourself of this, that this, what I have on the right hand side is simply S of rho prime. Okay. So this is negative trace. So I have a double sum here, but now I have this within the log, right? I have log sum over j pj rho pj. Actually, yeah. Well, maybe let me not expand this. That is not helping my case because I want to convert everything to rho prime, right? Okay, so let me instead, you also use the fact that pi squared is equal to pi. So this is what I have used here. So in the next step, I'm going to use the fact that pi squared is the same as pi. So this sum over I pi, I'm going to make it into sum over I pi squared. I'm going to move one of the pi's to the other side. And then I'm going to use the fact that log rho prime actually commutes with pi. Okay. So let me note that fact. If you can't prove it yourself, I'll prove this tomorrow again. So log rho prime, not tomorrow, I mean Monday's class, commutes with pi for all pi. Okay. So this should simply follow from the fact that rho I is pi rho pi. Okay, so try to prove this. That will be a good exercise for you. So if you take my word for this, then the rest of the steps will just follow. I can now bring the pi here so that I will have minus trace sum over I pi rho pi and then log rho prime, because log rho prime commutes with pi. So I moved it around. And then sum over I pi rho pi is nothing but rho prime. So I have trace rho prime, log rho prime with a negative sign. And that is nothing but S of rho prime. So hence I have shown that S of rho is always less than equal to S of rho prime, simply by taking the relative entropy between rho and rho prime and setting that to be positive. Okay. And what is the equality case? The equality case happens. So where did the inequality come from? It's just, again, your relative entropy inequality, right? So equality if and only if rho is equal to rho prime. So we already discussed this. And if rho must be equal to this convex sum of the action of these projections, it must imply that either there is only one projector in that measurement, right? In which case it's really not a projective measurement, it's just a single outcome something. Or your rho must already be diagonal in this basis. And then what you will have is only one of these projectors will act, right, in a non-trivial way, and you end up with rho itself. So this must then imply that rho is diagonal in the pi basis. Okay, so let me stop here for today. And if you want, I can revisit this proof on Monday in the beginning of class. Monday will be an in-person class. So please come to HSB 210 at 2 p.m. on Monday, right? Yeah. Yeah, so I'll wrap up today's class with this. If there are questions, I can take that, and then we'll see you all on Monday. Questions? Stop sharing, is it? Yeah. So on Monday, we look at what happens to the von Neumann entropy under unitaries and what happens when you mix states further, concavity, etc. Okay. All right. So see you all on Monday.